These are the notes for Unit 4, Day 1 of Pre-Calculus. If you would like to see the warm-up, the review question, or any of the test questions we went over in class today, just look at the finished notes from today. So in class today, we are going to talk about polynomial functions. What makes a function a polynomial function, how to tell what its degree and end behavior are, how to graph them using transformations, or how to find their real zeros, which are another way of saying their x-intercepts or roots, and how to talk about the end behavior, turning points, and how to graph them and write the equation for polynomial functions. So what makes something a polynomial function, and what makes it not a polynomial function? So polynomial is just a way of saying many terms. So a polynomial is a function or an expression that has many terms. And for our terms, the terms have to have whole number exponents. What does that mean? So whole numbers are not fractions or decimals, so the exponents can't be fractions or decimals, and they can't be negative. So you can't have a x term with a negative exponent either. So they have to have whole number exponents. So like x squared, x to the third, x, things like that. What you can't have is you can't have things like x to the 1/2, x to the -2, x to the 1.5. Those don't work. So to be a polynomial expression, you're going to be adding and subtracting terms that have whole number exponents. So if we look at the first example, A, we have 5x to the third minus 1/4 x to the second minus 9. That is a polynomial expression. All of the terms have exponents that are whole numbers. 9 is just a constant, so that guy is okay as well. Let's look at the next one. F of x equals x plus 2 minus 3x to the fourth. That's also a polynomial expression or a polynomial function. If we look at the next one, g of x equals the square root of x. If you guys remember, the square root of x is the same thing as x to the 1/2 power. That's not a polynomial expression because the x has an exponent that's a fraction. Let's look at the next one. D, h of x equals x to the second minus 2 over x to the third minus 3. Well, remember, if you have an x expression in the denominator, that means it technically had a negative exponent, so this is not polynomial either. We call that a rational expression. Rational expressions are expressions that look like polynomial fractions. So the numerator is a polynomial and the denominator is a polynomial, but the entire expression we call rational. G of x equals 8. That's a linear expression. It's a horizontal line, but linears are a type of polynomial expression, so that would count as well. So we could call that polynomial, even though it's linear. It's a constant expression. And then our last one, h of x equals negative 2x to the third times x minus 1 squared. If we were to multiply this all the way out, all of the terms that I would get would be whole number exponents, and we would be okay. So that would also be a polynomial expression. So that's how you can tell if a function is polynomial or not, just based on its function, its equation. How you can tell on a graph, a polynomial function's graph looks like a smooth curve, meaning that there's no sharp edges and it continues forever. So there's not going to be any breaks in the graph. So there's no breaks in the graph. It has tails. So notice it has the tails here and here. What makes it not a polynomial graph? So this is a bunch of things that make it not polynomials. So a corner looks like a corner of a square, right? So if a line meets another line, like in an absolute value graph, that would be a corner. It also could have cusps, which means that's a curve meeting another curve. So like a parabola meeting another parabola, that would be a cusp. So if a graph has a corner or a cusp, it's not a polynomial function because it's not a smooth curve. Also, if it has any breaks in the graph, so notice right here that would be a break in the graph. We call that a jump. So it's jumping from one point to another. That is not a polynomial function. Or if it has a hole, so there's a break in the graph where it just keeps it's going and then it stops with the hole, that also means that it's not going to be a polynomial function. So polynomial functions are smooth curves that have tails. So some examples of polynomial functions that you have already learned about is 3x. So lines are polynomial functions and the degree is 1. So when we're talking about the degree of a polynomial function, we're talking about the highest exponent of all the terms. So the term with the highest exponent would give it the degree of the polynomial. So since this is 3x and x is to the first power, that would be the degree of the polynomial. So if it is a degree of 1, we call it a linear polynomial. And this would just start at 0 and then go up 3 over 1. And that would be the graph of that polynomial function. Another one that we already know is the degree 2 is a quadratic function. And we graphed those in our last unit. So negative 5x squared would start at 0, 0, and then it's way narrower and it's sad. So that would be what the graph of that polynomial would look like. 8x to the third, we call that a cubic polynomial. And you remember cubics look like the snakes, and that 8 just makes it way narrower than normal. And then here's a new one. So negative 1/4 x to the fourth, and x to the fourth is called a quartic function. So if it has a degree 4, 4 is the highest exponent, we call that a quartic function. And let's just go on Desmos and see what this guy looks like. So if we're on Desmos and we want to graph negative 1/2 x to the fifth. Now notice that, oops, it's x to the fourth, isn't it? Sorry. That also looks like one that we've already had. It kind of looks like a parabola, but do you notice that the top of the parabola where the vertex is looks flatter than our normal graph? So an x to the fourth parent function would kind of look like a parabola, but it kind of is flatter at the vertex than a normal quadratic function. So the higher even the exponent is, so x to the fourth, x to the sixth, x to the eighth, it just makes it flatter and flatter. It looks flatter and flatter along that line. So if you have negative 1/2 x to the fourth, that's going to make it wider than normal and sad. So it's just wider than normal, so it's going to look even flatter up top than a normal parabola. But that's what the parent function for an x to the fourth graph looks like. End behavior. You guys might remember talking about this in Algebra 2. End behavior is what the tails are doing. So what direction are the tails pointing in? And then the tails of the graph are the ends. So what direction are the tails pointing in? Are they going up? Are they going down? Which way are they pointing? So the easiest way to remember the end behavior is even versus odd and positive versus negative. So let's start with our even end behavior. So if the degree is even, so remember the degree is the highest exponent. So if the degree is even, you've got two options. And I always remember this with the parent function x squared. And this is going to be true for any even degree. So if I have x squared and I wanted to graph it, it would just be a happy parabola, correct? And so the end behavior, well, look at those two tails. The tails are rising and rising. So we say the end behavior is rises and rises, or you can say up and up, or it's going to infinity and infinity. Those are different ways of talking about the end behavior. So if it's an even degree and the leading coefficient is positive, the end behavior is up, up, rises, rises, or goes to infinity and infinity. What if it's an even degree and it's negative out in front? So y equals negative x squared. Well, we know that that's going to be a sad parabola. And we know that the end behavior for the sad parabola, well, look at those two tails. Those two tails fall and fall. So the end behavior is falls, falls, or you can say that they go to negative infinity, or it's down, down. So that's what happens if it's an even degree, so x to the second, x to the fourth, x to the eighth, x to the 10th. Any even degree will follow those same rules for the end behavior. If it's an odd degree, so like x to the third, and we already know what x to the third looks like, right? It looks like a snake. So what's his end behavior? Well, on the left side, it falls. And on the right side, it rises. So it falls, then rises. And that would be the end behavior for positive x to the third. And that's going to be true for any odd degree polynomial. So x to the third, x to the fifth, x to the seventh. That'll be true for any of those with a degree that's odd. And then if you have y equals negative x to the third, well, I'm reflecting it over the x-axis, so the pieces that were up go down, and the pieces that were up go down, or that were up go down, and that were down go up. So it's just a reflection. And so this one, on the left-hand side, it rises, or it's going to positive infinity, and on the right-hand side, it falls, or it's falling to negative infinity. And so that would be one way of telling the end behavior for polynomial functions. You look at the degree, so the highest exponent, and decide if it's even or odd. And then you look at the leading coefficient and decide if it's positive or negative. And then from there, you can talk about the end behavior of the polynomial. So graphing polynomials using transformations. So this would be the same thing for parent functions. So we just looked at the parent function x to the fourth on Desmos, and it looked a little bit flatter than a normal parabola. So let's look at what x to the fifth would look like as a parent function. And then we graph it with transformations the exact same way. So x to the fifth. So notice he looks like x to the third. He's just going to be a little bit flatter at the vertex than the x to the third function. So just like the quartics or the x to the fourths were flatter at the vertex, the x to the fifth is going to be a little bit flatter at its middle point at 0, 0. It flattens out a little bit there. So now, if we were going to graph this using transformations, a couple different things happened to this graph, right? It went up 2, it went to the right 1, and then it was reflected. And it was an up-down reflection, or reflected over the x-axis. So if I wanted to graph, I'm going to take that parent function, and I'm going to move it up 2 and to the right 1. So that would be the new center. And then it's a reflection from up down. So instead of falling and then rising for the end behavior, it's going to rise and then fall, and then it's going to just be flatter there. And it's going to look like that. And so you can graph any of the polynomial functions by first figuring out what the parent function looks like, and then using the transformations to graph it. Another thing that we could talk about for polynomial functions are the zeros, which is another way of just saying x-intercepts. So other ways of saying x-intercepts are zeros and roots, which are right before that. So if I say find the x-intercepts, or find the zeros, or find the roots, it means the exact same thing. So x-intercepts, remember, are when y is 0, or where the graph crosses the x-axis. So if we look at this first picture, the zeros, or the roots, or the x-intercepts for this graph, would be the point -3, 0, 1, 0, and 4, 0. So those are the roots, or the zeros, or the x-intercepts of that function. If I look at the next one, where it touches the x-axis are at -2, 1, and 3. So the x-intercepts, roots, or zeros of this function would be -2, 0, 1, 0, and 3, 0. And then if I look at the next one, my x-intercepts would be at -2, -1, and 1. So -2, 0, -1, 0, and 1, 0 would be the x-intercepts, roots, or zeros of that function. How do you find it if they give you the equation? Well, remember what we just said. You set the y equal to 0, and remember f of x is just another way of saying y. So 0 equals 3x times 2 minus x times x plus 4. Well, since I have a product, I'm taking 3x times 2 minus x times x plus 4, I can use the zero product property, or I just set each piece equal to 0. So either 3x is 0, 2 minus x is 0, or x plus 4 is 0. So it's in the factored form. So we factored and we solved. So either x is 0, x is 2, or x is -4. So that means if I were to graph that, I would have x-intercepts at 0, 2, and -4. What would the end behavior look like for this graph? Well, I would have to multiply it out, and I really only care about the biggest exponent when I multiply it. So I'm just going to multiply these guys together. So 3x times -x would give me -3x squared, and then times another x, I would have -3x to the fourth would be the term with the biggest exponent. Well, that's an even degree and a negative leading coefficient. So if you think about it, that would be like a sad parabola. So my end behavior is going to be down, down. Well, if this graph has to pass through the points and it's down, down, sorry, it's not x to the fourth, it's x to the third. Good multiplication, Miss Hefflinger. So 3x times negative x times x is negative x to the third. So this is actually an odd function, and it's negative. So if you remember from our end behavior, it would be a snake that would start up and then go down. So let's erase this. So this graph is going to start up and then go down, but it has to cross through the x-intercept. So it's going to go through each of those points. So this could be a sketch of what that graph would look like. It's not a very accurate sketch, but it would be a sketch. So the end behavior would be up, then down. So it has to start up, and then it has to pass through those x-intercepts, and then eventually go down. So sometimes your roots happen more than once. So the multiplicity of the roots is how many times x is equal to the same number. What does that mean, Miss Hefflinger? So for instance, if I had f of x equals x minus 3 squared times x plus 4 cubed. If I wanted to solve that, I could write x minus 3 twice, correct? And I could write x plus 4 3 times. So the multiplicity of the roots, so the roots would be, or the x-intercepts would be x equals 3, x equals 3, and then this one would be x equals negative 4, x equals negative 4, and x equals negative 4. Well, how many times did x equal 3? So since it equaled 3 twice, we say that this has a multiplicity of 2. Since x is equal to negative 4 3 times, we say it has a multiplicity of 3. Well, what does multiplicity mean in terms of the graph? Well, in terms of the graph, I know that I have x-intercepts at 3 and at negative 4. If a graph has a multiplicity that's odd, then that means that when that x-intercept happens, the graph actually passes through the x-axis at that point. So it'll actually pass through the x-axis at negative 4. But when you have an even multiplicity, so notice x equals 3 happens twice, what happens there is that your graph will approach the 3 and then hit the 3, but instead of going through the x-axis, it's going to bounce off the x-axis and come back up or go back down, depending on where it was to begin with. So if I multiplied this out, x times x times x times x times x, the degree of that polynomial would be 5. So it's an odd degree, and it's positive, so it's an even coefficient. So like a snake, it's going to start down and end up. So at x equals negative 4, it happened 3 times. So that means the multiplicity, since it's odd, it means that it's going to pass through negative 4. And then my parabola, and then it's going to come up. And then notice when my x-intercept is 3, it's a multiplicity of 2. 3 happened twice. So instead of going through at 3, it's going to hit 3 and then not pass through the x-axis, but just kind of bounce off the x-axis at 3. So this is just a rough sketch of what that would look like. But if I were to graph this graph on Desmos, so x minus 3 squared, and then x plus 4 cubed, notice, I didn't sketch it perfectly, but notice that it crosses through at negative 4 and then it bounces off at 3. And so that's kind of a sketch of what that graph would look like. I didn't do it perfectly, obviously, but it was a general sketch. So graphing polynomials using intercepts, points, and end behavior. So let's start with the intercepts. So the intercepts are when the y value is equal to 0. So x times x plus 2 times x minus 1 squared. So x minus 1, x minus 1. So the x-intercepts are going to be 0, negative 2, 1, and 1. So 1 has a multiplicity of 2, which means that it's not going to pass through the x-axis there. It's just going to bounce off the x-axis there. So I have an x-intercept at 0, at negative 2, and at 1. If I were to multiply this out, I would have an x squared, I would have an x and an x. So this would mean an x to the 4th. And remember, an x to the 4th is even, and it's positive, so it'll be like a happy parabola. So the end behavior will be up and up. It's going to bounce off at 1. So it's going to start up. It's going to pass through 0, 0, and then at this point, it's going to bounce off 1 and then keep going. So that's a rough sketch. So we used end behavior, we used intercepts. We could find another point on the graph to make it a little bit more accurate. So if I found what's happening when x is equal to -1, that'll help me figure out how low this graph is going to go. So if I found f at -1, I would just plug -1 in. So -1 times -1 plus 2 times -1 minus 1 squared. So this would be -1 times 4, which is -4. So if I wanted to make this a little bit more accurate, I know that at -1, it's at -4. So we could go all the way down there and then pop back up. And then we know that it's going to hit, and then it's going to keep going. So let's see how close we are. We also could have found a point at 1/2. X equals 1/2 would have been a good one to do. So let's see how close we were this time. So x times x plus 2 times x minus 1 squared. We were pretty close. It's not a terrible looking graph. All right. So turning points. So turning points on the graph are what you would view as the peaks and the valleys on the graph. So like if this is my guy, that peak and that valley, we would call those the turning points. How many turning points a graph has? So the most turning points that a graph could have is 1 less than the degree. So the most turning points of a polynomial is the degree minus 1. So it's 1 less than the degree. So notice x squared, if you were to graph x squared, it's a happy parabola, and it has 1 turning point at the vertex. And remember, the degree is 2, 1 turning point, 2 minus 1 is 1. So that would be the turning point. X cubes could have at most 2 turning points. So that would be an x cubed could have at most 2 turning points. X to the 4ths could have at most 3 turning points. So it could have a peak and 2 valleys, or 2 valleys and a peak, and then so on and so forth. X to the 5th could have at most 4 turning points, etc., etc. So the turning points on the graph are the peaks and the valleys, which we also call local minimums and local maximums, if you remember. And the most turning points that you could have would be 1 less than the degree. You don't have to have that many turning points, but that would be the most that you could have on a polynomial graph. All right, so which of these graphs are polynomials? So if you remember, a polynomial graph can't have any breaks. So this first graph, A, has a jump. So that's not polynomial. B is a smooth curve. It doesn't have any breaks in the graph, and it doesn't have any corners, sharp corners or cusps. So this is polynomial. C is not polynomial because it has that corner right there. So this is not polynomial. And then that last graph could be polynomial as well because, again, it's a smooth curve and there's no sharp corners or cusps. Then it wants us to list the real zeros. So the x-intercepts. So this one would have real zeros at -2, 1, and 2. So this guy has zeros at x equals -2, 1, and 2. And then what's the smallest degree, or state the degree this polynomial could have? Well, this polynomial has 2 turning points, and so 1 fewer than the number of turning points. The smallest degree this polynomial could have would be x to the 3rd because it has 2 turning points. This polynomial over here has zeros at, so it has zeros at -2, x equals -2, and x equals 1. And then again, this guy has 1, 2, 3 turning points. So 3 turning points, the smallest degree this could have would be x to the 4th. All right. What could be the graph of x to the 4th plus ax to the 3rd plus bx squared minus 5x minus 6? All right, let's start with the degree. So it's x to the fourth, so it's an even degree, and it's a positive leading coefficient. So my tails should be up and up based on the end behavior information. So I know now it can't be graph D, because graph D would have to be negative x to the fourth. Since it's x to the fourth, the most turning points that I could have is 3. So this one right here has 1, 2, 3, 4, 5 turning points, so it can't be that graph. Now it's between A and B, graph A and graph B. They're telling me that A has to be bigger than 0 and B has to be bigger than 0. So both of these are going to be positive and positive. Okay, what could we find? So for x-intercepts, we would let y equal 0. So if I let 0 equal x to the fourth plus ax to the third plus bx squared minus 5x minus 6, that doesn't look like super fun to solve. But we also have the y-intercept, which we haven't talked about today. How do we find the y-intercept? We let x be 0. So if I let x be 0, the y would be 0, 0, 0, 0, and then the only thing that would be left was negative 6. Well, which one of those graphs have a y-intercept that's below the x-axis? Well, this has a positive y-intercept. This has a negative y-intercept. So the graph that would match that would have to be B based on the end behavior, turning points, and y-intercept. All right, so finding a polynomial based on points given. So I know that this polynomial has x-intercepts at x equals negative 2, x equals 0, and x equals 2. But notice right here, what's true about the x-intercept at x equals negative 2? Notice how it's bouncing off the x-axis there? That means that the multiplicity at negative 2 is at least 2, because it has to have an even multiplicity to bounce off the graph. So those could be my zeros or my factors. But remember to find those. If you were actually going to solve, you set them equal to 0 and solve. So if I had x equals negative 2, if I want to get that back to equal to 0, I would add 2 to both sides. And so that means that one of my factors had to be x plus 2 to make that happen. Since that had a multiplicity of 2, I could write x plus 2, x plus 2. Now, x equals 0, well, x equals 0, so subtract 0 from both sides. So x minus 0 equals 0. That's just x. You could also write it as x minus 0 if you wanted to. And then this last one, subtract the 2, and x minus 2 would equal 0. So x minus 2 could also be a polynomial, or sorry, could also be a factor. Now, we also have this point right here. So they're giving us a last point. So we're just going to put an a out in front so we can solve for that a. So I know the point negative 1, positive 6 also has to pass through this polynomial. So I can plug in negative 1 for x and 6 for y to solve for that a out in front. So this is going to be 6 equals a times negative 1 times negative 1 plus 2 times negative 1 plus 2 times negative 1 minus 2. So this would be 6 equals negative a times 1 times negative 3. So 6 equals 3a. So a could be 2. So our polynomial function could be y equals 2 times x plus 2 squared times x minus 2. So that could be a polynomial function that could match the graph. So let's just test that on Desmos and see how close that actually matches our picture. So we had 2x times x plus 2 squared times x minus 2. And then if we look at that compared to our other graph, it looks pretty decent. So we have it down there at negative 19, and notice that on our graph it looks like it's at negative 19. We have negative 2, 0. We have that. We also have negative 1, 6 if we scroll up to that. So, and if I spread it out, I could make it look a little bit wider like that one. So that would be one expression that could match that graph. All right, gentlemen, your homework is from 4.1. If you have any questions,